Today what we're going to talk about are types of chemical reactions. And if you're looking in the Tro textbook, he talks about two different ways to discuss reactions. And the way we're going to start is actually what's at the end of chapter 7. And we're going to talk about classifying reactions based on what the reactants and products do. So remember last time we were talking about balancing equations. So this is more on equations, and we'll practice balancing along the way as well. So what we're going to talk about today are types of reactions. And we're basically going to cover 5 different types of reactions today. One, we're going to cover synthesis, sometimes called combination reactions. We're going to cover decomposition reactions, single replacement, double replacement, and combustion. This is only one of the ways that you can categorize chemical reactions. When we're all done going through these 5 different systems, I'm going to also talk about redox, oxidation reduction reactions, and some of these can be classified as oxidation reduction reactions in addition to one of these 5, and we'll talk about that at the end, not to overwhelm it all to begin with. So to start out with, we're going to talk about synthesis reactions. So in a synthesis reaction, the main thing to know is that what's going to be true is you're going to have more than one reactant. But you're only going to form one product. So the key to seeing that something is a synthesis reaction is the fact that you only have one product. So some examples would be one we started out with balancing equations. If you take hydrogen and oxygen and you form water, this would be an example of a combination or a synthesis reaction. Notice there are 2 reactants, hydrogen and oxygen, and only one product, water. And of course, now that we know how to balance equations, every reaction we write, we should balance. So going through that, we have a hydrogen molecule and an oxygen molecule. And over here, we have a water molecule, and we need to have the same number on both sides. So right now I have 2 hydrogens and I have 2 hydrogens, and on this side I have 2 oxygens, and over here I only have 1. So I'm going to need to put a 2 over here, and I'm going to need to make 2 of these water molecules, in which case now I have 2 oxygens, but I'm going to need to add 2 hydrogens. So I have a total of 1, 2, 3, 4 hydrogen atoms and 2 oxygen atoms on both sides of my equation. The general formula you would see for synthesis reactions is sometimes A plus B turns into C. Again, the key here is that there is only one product. So other examples of synthesis or combination reactions could be something like this. SO2 gas plus oxygen gas turns into SO3 gas. This is also a combination or a synthesis reaction, again, because there's only one product that is formed. Some of these you would really not be able to predict the products of, and for instance, this one I would have to go through and show you. But if we tried to balance this equation, going through, we have 1 sulfur and 1 sulfur, and on this side we have 4 oxygens, on this side we only have 3, and so let's just try to put a 2 in front. If we put a 2 in front of here, so now at least we have 6, which is more than over here with 4 on the oxygens. We now have 2 sulfurs, so I'd need 2 of these. Now I have 2 sulfur, I have 2 times 2 or 4 oxygen. Over here I have 2 oxygen, my total is 6. And over here my total is 6 oxygens. So that would be a balanced equation and a synthesis reaction. If your synthesis reaction is involving a metal and a nonmetal, something like aluminum plus oxygen, I could ask you to predict the product for that because you know how to write formulas for ionic compounds. And remember, an ionic compound is always going to be a metal and a nonmetal. So some of these you could be asked to predict a product of, and you'd have to go through the whole process in the naming. Remember that aluminum's in group 13, so it has 3 valence electrons. It's going to be +3. Oxygen is in group 16, so it has 6. It's going to gain 2. And so now we need the formula for aluminum and oxygen. We need to get a common number. Common number is 6, so I'm going to need 2 aluminum, 3 pluses, and 3 oxygen, 2 minuses, but I'm going to write that as Al2O3. So some of these I could ask you to predict, but I'm only going to ask you to predict for the ones that form ionic compounds. Forming ionic compounds from a metal and a nonmetal. And this equation, of course, is not balanced either. So going through, if I have 1 aluminum on the reactant side, I have 2 on the product, I would start out with a 2 here. Looking at oxygen, I know I have a problem. I have 2 on my reactant side, and I have 3 over here on my product side. I'm going to, again, go for my common number of 6. So I'm going to need to make 2 of these. I'm going to need 3 oxygens, and now I'm going to have to change my 2 into a 4 and balance it. So synthesis reactions are fairly straightforward. If it's not a metal and a non-metal, the product will be given to you. You do need to be able to recognize them. And again, the key is only one product. The second type of chemical reaction we're going to talk about are called decomposition reactions. Decomposition reactions are sometimes thought of as the reverse of a synthesis or combination reaction. In general, what's going to be true is you're only going to have one reactant, and it's going to produce 2 or more products. The way that you identify a decomposition reaction is the fact that there is only one reactant. So these I would not really necessarily expect you to predict products of, but you should be able to identify a reaction and balance the equation for a decomposition reaction. Some examples would be, if I took potassium chlorate and heated it up, it would turn into potassium chloride and oxygen gas. So this is a decomposition reaction, again, only one reactant turning into 2 or more products. And if I was going to balance this equation, I have a potassium and 1 potassium and 1 chlorine and 1 chlorine, but again, that 2 and 3 oxygen thing, so I'm going to need 2 potassium chlorates producing 3 oxygens, and then I'm going to need a 2 in front of the KCl as well. Another example of a decomposition reaction would be heating up sodium bicarbonate. Oh, sorry, that's a C. If I heat this up, I'm going to produce sodium carbonate, water, and carbon dioxide. This one looks a little more complicated. Of course, I would not ask you to predict the products for this, but you should be able to recognize it as a decomposition reaction. And again, the key, there's only one reactant. So you need to balance this equation as well. So going through, I have 1 sodium atom. On my product side, I have 2. So I'm going to start out putting a 2 here. I now have 2 hydrogens, and I also have 2 hydrogens here. I now have 2 carbons, and I have 1 carbon here and another carbon here, so that's good. I have 2 times 3, I have 6 oxygens. On my product side, I have 3, I have 4, 5, 6. So that is balanced by just putting a 2 in front. So combination or synthesis reactions and decomposition reactions are not necessarily all that tricky, but you do need to recognize them. Key, synthesis, only one product. Decomposition, key, only one reactant. So we move forward, the next ones are going to be a little bit more involved. Third category I wanted to talk to you about are single replacement reactions. Single replacement reactions are a little bit more involved, and I'm going to make a separate video for how do you predict products of these so that this is not overwhelmingly long. But in general, the reaction is going to look like this. A plus BC is going to turn into AC plus B. So what happens in here is you start out with an element and a compound. And when you look at this compound, it's typically going to be ionic, although it doesn't necessarily have to be. But a compound, remember, has 2 elements. The ones we're going to deal are going to be binary compounds. And so there will only be 2 elements. So what's going to happen is the elements are going to switch places. I think this is sometimes easiest to show by an example. So if I were to show you a reaction such as zinc solid plus copper chloride. Looking at this reaction, it's going to be a single replacement reaction because I have, one is an element, zinc in its elemental state, and then I have copper chloride. And remember, AQ is meaning dissolved in water. We're going to come back to solutions and how things dissolve in a bigger example explanation video clip, but right now I just want to kind of get through the reaction formats. So what's going to happen here is this is a metal, zinc, and copper is a metal, and chlorine, of course, is a nonmetal. In this case, what's going to happen is the two metals are going to switch places. The two metals are going to switch places. Now, when you do this, you have to be very careful of their charges. In this one, copper is already 2+, and remember, zinc is one of the ones I asked you to remember, that zinc is always 2+. So when they switch partners, it's not really going to be too bad. I'm going to end up with zinc chloride, aqueous, and then I'm going to get copper solid as my other product. And this reaction is balanced as written. Notice that what's happening though is zinc is my A, copper is my B, chlorine is my C. So I have A plus BC, and what I end up getting over here is A to C and B. So these are a little bit harder to identify. So in the beginning, I would say to practice just picking out single replacement reactions, and then watch the later video of how to actually go through and predict products. Let's just try one more. So in a separate reaction, what if I showed you sodium solid and we just put it in water? Now I'm going to cheat and write water as HOH. The reason I'm writing water as HOH is because I want sodium to be my A, I want hydrogen to be my C, but I want hydroxide, this polyatomic ion, to be my C. And so what's going to happen here? I'm going to switch places between sodium and hydrogen. And so I'm going to end up with Na, which remember is in group 1. So it's going to be +1. And I'm going to end up over here with hydrogen is also in group 1. So it is 1+. So OH is going to be 1-. So these two are going to come together and form sodium hydroxide. You don't know right now, but I'll explain to you later. It will be aqueous. I'll tell you how you'll know that in a little bit. What will be my other product? So hydrogen is going to go off on its own, right? Because these two are switching places. And so hydrogen has to come off by itself, but I don't want to just write H. Why would I not write H? It's true that that's the element, but hydrogen, remember, is one of the 7 diatomic elements, so it's going to be H2. Hydrogen is diatomic. There's a whole bunch of little details that you have to worry about in doing these reactions. Practice is really the key to making it work better. Remember, the diatomic elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So whenever you produce these as elements, you need to remember to write them as diatomic molecules. Now this equation is not balanced as it's written. Let me rewrite it so it doesn't look as messy. Sodium plus HOH, which water would be a liquid, it's going to give me NaOH aqueous and H2 gas. If I go through, I have 1 sodium atom, 1 sodium atom, I have 1 hydroxide, I have 1 hydroxide, but here I have 1 hydrogen and here I have 2. So I'm going to need to put a 2 here. If I put a 2 there, now I need 2 hydroxides, so I'm going to need a 2 here, but now I need 2 sodiums, so I'm going to need a 2 there, and it would now be balanced. We're going to come back in an individual video and talk about single replacement reactions and how do you know what things can replace others. There is another type that can actually replace the anions. If you notice the 2 that I showed you, it's the cations that change places, but it is possible to change the anions, and I'll show you in a separate video some more examples. So that's it for right now in single replacement reactions, but we'll do more detail later. The 4th type of reaction I wanted to show you is called a double replacement. Double replacement reactions are going to be AB plus CD And so in this, we're going to have a binary compound and a compound. So this is going to be different. The way that you recognize this is that you're going to have two different compounds reacting. And what's going to happen, remember, you always write the positive first, and so they're going to switch partners. The positive A is going to go with the negative D, and the positive C is going to go with the negative B. It's a little confusing because when you write it, you always put the positive first, so I'm going to keep C in front. So if you notice, all that really happened is that they switch partners. Double replacement reactions can actually be a little bit more confusing in that there are actually three different categories of them. You can have precipitation reactions. You can have gas evolution reactions, and you can have acid-base reactions, acid-base neutralization reactions. We're going to go into each one of the three of those and how you predict products in a separate video. So that way it's not overwhelming and you can concentrate on just one type. But let me just give you a couple of quick examples of double replacement reactions so you can get an idea of what they look like. And then in a later video, we'll talk about how do you actually get to products. So here are some examples of double replacement reactions. If I were to take barium hydroxide dissolved in water and react it with sulfuric acid, also dissolved in water, what would I get as products? If I think about this, barium hydroxide is really going to be barium ions. Barium's in group 2, so it's going to be +2. Hydroxide is -1. And over here, you can think about the hydrogen as an ion. They're going to be 1+, and sulfates are going to be 2 minuses. This is in group 1. This is in group 2. This you just need to remember. And this one you also can remember, or you can figure them out, of course, from their cation. If you know that the barium is +2, and you have 2 hydroxides, each one of these must be -1. So if you wanted to write it all out, I would actually have barium hydroxide, hydroxide, and I'd have hydrogen, hydrogen, and sulfate. So in a total, I would have 1, 2, 3, 4, 5, 6 different ions in there. When they switch partners, what's going to happen is the barium is going to go with the sulfate, and the hydrogen is going to go with the hydroxide. And so barium is +2, sulfate is -2. And so all I need to write for my formula is BaSO4. Now what comes here is I'm going to tell you that it's a solid, but right now you would not know that. I'm going to tell you later how you would figure that out. What's my other product going to be? Well, I have hydrogen 1+ and I have hydroxides 1-, and so I'm going to put them together, and I'm going to again cheat and write it as HOH, but most of the places are just going to write that as H2O. Now, I didn't just have 1 hydrogen and 1 hydroxide, I had 2 of each, so I'm going to actually need to put a 2 in front of that to balance my equation. So these get to be a little bit more complicated, there's no doubt about it, and people struggle. So in a separate video, we're going to talk about double replacement reactions and how you can go through them and figure out exactly what the products are step by step, and there's some definitions along the way. Let me just show you one more before we move to the last kind of reaction. And let's just say we had K2S aqueous potassium sulfide, and we react it with iron 3 chloride. And I ask you, what do you think we're going to get as products? Well, potassium sulfide, potassium's in group 1, sulfur's in group 6, iron 3 chloride, it's going to have +3 for iron, and chloride's in group 17, so it's going to be -1. So remember, I'm using the group numbers to get those charges. The iron, I'd have to figure out going backwards. I have 3 chlorides, each one is -1 for a total of -3. So my iron is therefore +3. So what's going to happen is my potassium is going to go with my chloride. I have potassium 1+, chloride 1-, so it's just going to be KCl. I know it's aqueous, but you don't know that yet, but I'll show you again in the future how you're going to figure that out. My other one is going to take iron 3 as my positive, and I got to mix it with sulfur, my minus. Now I got a +3 and a -2, so remember I need to get the same number of charge in both positive and negative, and so what I really need is this, right? So that I have a total of 2 of these and 2 iron plus 3s and 3 sulfur 2 minuses in order to balance out the charge, but I'm going to write that as Fe2S3. And I know that that's a solid, and again, I'll tell you how you're going to figure that out in a later one. So this equation is not balanced. On one reactant side, I have 2 potassiums, but on my product side, I only have 1. So I'm going to need to put a 2 in front of here, and what I'm really going to need is another one of the potassium chlorides. So that will work out fine for the potassium, but what about the chlorides? I don't think that's going to work quite yet. If you look on the reactant side, I have 3 chlorides, and on my product side, I only now have 2. So this 2 is probably not going to last. If I really want to go through this, what do I really need to get going is I need to have 3 sulfurs. I know that from looking at this. And so over here I have 1 sulfur and over here I have 3. So I know I'm going to need a 3 here. That's going to change my number of potassiums to 6. So this is now going to be 6. I'm not going to draw out 6 of them. That's just too many to write. But now I have 3 times 2, 6 potassiums, and I have 3 times 1, 3 sulfurs. I now have 6 potassiums, and I now have 3 sulfurs. What about the chlorides? On this side, I also have 6, and on my reactant side, I only have 3. So I'm going to need a 2 in front. I now have 2 irons, but on the product side, I also have 2 irons. So my final balanced equation is going to be 2, whoops, sorry about that, messy, 2 potassium sulfide, so 3 potassium sulfides plus 2 iron 3 chlorides will produce 6 potassium chlorides and 1 iron 3 sulfide. So these, as you can see, this wasn't even that bad of a reaction. It started out with monatomic ions. We're going to go through and practice a few other in a separate video, but again, for right now, what I'm looking for you to pick up the pattern of AB plus CD is going to AD plus CB. That's the general pattern that I'm looking for. To practice these, I put up on the module for this week a URL that has a practice where it's just showing you reactions. You predict what kind of reaction and you can practice balancing them. It's not asking you to predict any products. So it's just going along with what we're doing right here in this video. The 5th type of reaction I wanted to talk to you about are called combustion reactions. Combustion really means burning in the presence of oxygen. And the most common things that can burn are organic compounds, and organic compounds all have carbon and hydrogens and sometimes oxygen. So for example, when we burn natural gas, which is methane, I could write methane plus oxygen, and this would now be a combustion reaction because I'm just burning it or reacting it with oxygen. When you have an organic compound and only carbon, hydrogens, or oxygens mixed in here, and all you have is carbon, hydrogens, and oxygens here, and you get complete combustion, the products are always carbon dioxide and water. I'm only going to ask you to know for organic compounds the combustion products, but you can combust things that are not organic. You just have to burn them in the presence of oxygen. Your textbook has a couple of examples, but they're not overwhelmingly too overwhelming to get through. You could also think about some of them as being single replacement reactions, but I didn't want to make that comparison quite yet. So here's a last example in this video. Let's do one other combustion reaction. So if I told you we had C3H8O and we were combusting it with oxygen to predict the products will always be carbon dioxide and water. And then all you need to do is balance your equation. Balancing my equation, I have 3 carbons, so I'm going to put a 3 here. I have 8 hydrogens, so I'm going to put a 4 here. Now I'm going to tally up my oxygens. On this side, I have 6 and I have 4 for a total of 10. And on this side, I'm going to have a problem because this is odd. And so I can't turn odd into even just by adding more to it. So I'm going to right away put a 2 here. When I put a 2 there, that's going to change this to be 6. That's going to change that to be 8. And now what I'm going to have over here is not 6 but 12, and not 4 but 8. And what I'm going to really have is 20. I can work with 20 now because this over here is going to be 2 oxygens. And I need 20 for a total, so I got to figure out how can I get 18 from here, and what I would need is a coefficient of 9. So my final balanced equation would look like this. And you can read this. I need 2 moles of C3H8O plus 9 moles of oxygen to produce 6 moles of CO2 and 8 moles of water. Or I could talk about individual molecules and say 2 molecules of C3H8O react with 9 molecules of oxygen to produce 6 molecules of CO2 and 8 molecules of H2O. So just as a summary, we talked about 5 different kinds of reactions. We talked about synthesis. And remember, synthesis, we're going to be A plus B turn into C, only one product. We talked about decomposition. Decomposition is when one thing turns into 2 or more. And the key is there's only one reactant in decomposition. We talked about single replacement, where A is going to react with BC, and A and B are going to switch places. And then we talked about double replacement. AB reacts with CD, and they switch partners, and you get AD plus CB. And again, C is written in the front because it's the positive. And then we talked about combustion. And so carbon, hydrogen, oxygen plus oxygen will always form CO2 and water. So for right now, if you can look at the reactions at the end of the chapter, and also the practice page that I posted, and just be able to identify reactions as these 5 types. And then in the future videos, what we're going to do is talk about how do you predict the products for single replacement and double replacement, and go through those in detail. That's it for now. Hope everything's going well.